Hi everyone, welcome back. Today we're going to start with chapter 16, acids and bases. So, acids and bases, probably we have a lot of them in our own households. We have some basic compounds, especially cleaning agent, that have a basic character. And we know acids, like orange juice or whatever, they're pretty acid. Vinegar, of course, also an acid. So what are we going to do in chapter 16? We're going to talk about today properties of acids and bases. Then we're going to calculate a little bit on solution, how acidic or basic is a solution. We do pH. And I'm going to talk about buffers. That's really important, especially for our own body. Conductivity do we have? We have some online worksheets, a few. Then we have a quiz. And then final is on chapter 16 and 18 together. All right, so acid. So one of the 5 flavors we know in our food: sweet, salty, bitter, umami. That's the pleasant, savory. So you see it in seaweed and sun-dried tomatoes. And the final one is sour. And there we have it, the acid, acidic. So in our food, well, the best example I think is a lemon or an orange, but also cola. Cola is really acid. It's a pH of 2.5, 3.5. It's really acid. So that's why they add a lot of sugar to cola. But it is really acid. Okay, some compounds that have a basic character, there are some cleaning agents like bleach or soap. They're pretty basic. So that in terms of pH, they have a high pH. When it's acidic, they have a low pH. We come later on in this chapter. So some definitions. So you can read in the book as well, but there are many definitions on acids and bases. The first one who came that was Mr. Arrhenius, and he said, acidic solution contains H plus and basic solution contains OH minus. So that's working pretty good. But we know N2O in water is also basic. But where's the OH minus? So we had to change the definition a little bit. And later on, Bronsford and Lowry came with a new definition, that an acid is a proton donor, and a proton is an H plus ion, and a base is a proton acceptor. So before you continue later on after finishing this movie, go to the presentation online and watch this movie. It has some interesting views on acids and bases. So, some definition again. Acids and bases. Assume we have an acid HA. And an acid is a proton donor. So, this H is going to donate it to H2O, forming H3O plus H minus. HA is losing a proton and H plus, and remaining is H minus. And these together, HA and H minus, we call that an acid base pair, conjugate acid base pair. So my acid donates an H plus to H2O, producing H3O plus, and remaining is H minus. That's for the acid. The base is a proton acceptor, so it accepts a proton from water, producing Hb plus, and what is remaining, H2O, is losing an H plus, is OH minus. So here we have the Arrhenius definition again. Base contains OH minus, and an acid contains H plus. And H plus is the same as H2O plus H plus makes H3O plus. So where you see H plus or H3O plus, it's the same. The difference is include water, yes or no. And water, that's important because acids and bases are always in water. So to repeat, HA, H minus, or HA minus is conjugate acid base pair, and here's the same B, HB plus, the base conjugate acid pair. The acid and the conjugate base are always together. What another definition about the strength of acids and bases. So if I have a strong acid, that means it dissociates completely in water. So we only have the forward reaction. So HA is losing all the protons to H2O, producing H3O plus. Base is all base except a proton from water producing OH minus. So we only have the forward reaction. And if I have a weak acid or a weak base, there's not a complete dissociation into ions, only partial. And there we see it's my equilibrium, as we learned in the previous chapter. So the difference between strong acids and strong bases, strong acid dissociates completely, while the weak acid, weak bases do not completely dissociate into ions. So that gives us an idea. If I have 1 mole per liter of a strong acid, I have more ions in a strong acid or strong base compared to a weak acid. That's important later on to calculate the pH of solutions. So strong acid base, complete dissociation, weak acid, not a complete dissociation. Water. Water is a little bit strange because look at these two. An acid plus water. Water accepts a H from my acid. So water acts as a base here. But when we have a base here plus water, and here water is donating an H plus to B. So water can act as a base and as an acid, and we call it amphoteric. So water can accept an H plus as a base, or it can donate an H plus. That is an acid. Why is that important? Here we have it. We have the equation H2O plus H2O in equilibrium, A3O plus, OH minus. So one water molecule is donating an H plus and the other one is accepting. And now we can have an equilibrium constant. So, and we know for water, the concentration of A3O plus is the same as OH minus because it's the ratio is 1 to 1. So an experiment showed that concentration is 1.0 times 10 to the negative 7. And now we can assess the value for my equilibrium constant. Concentration A3O plus times the concentration OH minus is 1.0 times 10 to the negative 14. And that's what we call the water constant. So remember, that's really important. We'll come back later in this chapter many times. So the water constant, 1.0 times 10 to the negative 14. So when do we call a solution acidic? Well, that's easy. When my concentration A3O plus is larger than the concentration OH minus, we call it acidic. When the concentration A3O plus is smaller than the concentration of OH minus, we call it basic. And when it's the same concentration A3O plus equals the concentration OH minus, we call it neutral. And as always, remember the water constant. Concentration A3O plus times concentration OH minus is 1.0 times 10 to the negative 14. So let's practice a little bit because we know this is the water constant. So when I have to calculate the concentration of A3O plus, when I know my OH minus, is it acidic or basic? So let's see how we're going to do that. So we can assess the concentration of A3O plus by the water constant divided with the OH minus concentration. So 1 times 10 to the negative 14 divided by a given concentration 1.0 times 10 to the negative 5. And we'll see it's time 1.0 times 10 to the negative 9 for A3O plus. And we see A3O plus concentration is smaller than OH minus, it's basic. Next one, other way around. Now I have 1.0 times 10 to the negative 9 MOH minus is acidic or basic. So we can assess again OH3 plus, the water constant over the concentration OH minus, and that gives me 1.0 times 10 to the negative 5 for H3O plus. And then H3O plus concentration larger than OH minus, acidic. Finally, when it is for the OH minus is 1.0 times 10 to the negative 7, what is it acidic or basic? We calculate H3O plus again, and then you'll find H3O plus as the same concentration, 1.0 times 10 to the negative 7. So now my concentration A3O plus is the same as OH minus. That means I have a neutral solution. Some names, some common acids and bases that are used a lot. So HCl, hydrochloric acid, HI, hydroiodic acid, HBr, hydrobromic acid. H2SO4, that's important, sulfuric acid. HNO3, nitric acid. HCl4, perchloric acid. And then we have some organic acids containing some carbon. Methanoic acid, also known as formic acid. Ethanoic acid, remember from our chapter Organic Chemistry. It has the C double bonded OH group, ethanoic acid, and that's what we call acetic acid. Ca3COOH, butanoic acid or butyric acid. Common acids. So guys, what I want you to do for next class is just study chapter 16.1. And next class we're going to calculate how acid or how basic is a solution. That was it for today, guys. Good luck, everyone. Bye-bye.